Hello, welcome to another module in this massive open online course. So, let us continue our discussion on joint entropy, that is we are looking at the joint entropy of two sources, that is h of x comma y. Okay. So, we are looking at the notion of joint entropy, okay, and we have seen that the joint entropy can be defined as h of x comma y equals, that is treating this as two dimensional symbol, summation over all I comma j, summation over all I j log to the base 2 1 over p of I j, where p of I j equals the probability x equal to si comma y equals rj. We have seen this joint entropy. We have also calculated from our example that hxy equals, well, that is equals 3.37 bits. This we have seen from example. Now, let us make an interesting observation. We have also seen the probabilities. If you remember, for the example, we have also computed the probabilities of the symbols. For instance, probability of S, we have seen that S naught, S1, S2, S3 are equiprobable. So, the probability that x takes any of these symbols, x is any of these symbols, is 1 by 4. Okay. For instance, probability x equals S naught equals 1 by 4. Further, we also come, for instance, the probability that y equals R3 equals 1 by 8. So, if we look at x and y individually, these are known as the marginal probabilities. So, we are also computed the marginal probabilities for x and y, correct. So, we know the joint probabilities p I comma j, that is what we have called probability x equal to si. So, we have also computed the marginal probabilities. For instance, probability x equals S0 equals probability x equals S1 equals probability x equals S2 equals probability x equals S3 equals 1 by 4. Hence, the entropy of this source is h of x corresponds to simply the entropy of a source with symbols with probabilities 1 by 4 each, correct. I use this notation to denote that there are basically 1 by 4 each. Okay, source with 4 symbols which are equiprobable. Okay, probability equal to 1 by 4 each, which means we have h of x equals 4 times 1 by 4 log 2 to the base to 1 over 1 by 4 is log 4, that is basically log 4 to the base 2, or so that is equal to 1 times 2 equals 2 bits. Okay. Similarly, we have computed entropy of y corresponds to the entropy of a source with the marginal probabilities. We have calculated the marginal probabilities. Probability of R0 is half, R1 is 1 by 4 R2 and R3 are 1 by 8 each. So, this entropy we already, so this entropy is half, let us just compute it once more, log to the base 2 1 over half, that is basically log to the base 2 of 2 plus 1 by 4 plus 1 by 8 plus log 1 by 8 log to the base 2 of 8. So, this is basically half plus half plus 3 by 8 plus 3 by 8 equals basically 1 plus 3 by 4. So, that would be 7 by 4, which is equal to basically 1.75 bits. Okay. So, we have calculated h of x and h of y from the marginal probabilities, the marginal probability mass functions. We have seen that h of x, that is entropy of source x, is 2 bits, entropy of y is 1.75. Now, you will observe something very interesting. Will realize two interesting properties. One, you can see h of x y equals 3.375, and this is greater than both h of x, which is equal to 2, and it is also greater than h of x y is also greater than h of y, which is equal to 1.75. So, we have basically h of x comma y is greater than h of x comma y is greater than or greater than equal to, rather greater than equal to h or y, and this property can be shown. And this is an interesting property. What this says is the joint entropy, that is joint entropy of two sources, is greater than or equal to the individual, right, the individual entropy of either source, correct. So, if I look at the joint entropy of two sources, the or basically the joint we said that entropy is nothing but a measure of information, right. It's means to quantify the information. So, the joint entropy of two sources cannot be smaller than the information in either source. So, when you are looking at two sources together, the amount of information they convey together cannot be smaller than the amount of information either source conveys in isolation. Okay. So, that is an important point, that is very intuitive, but it shows that this property follows through the definition of joint entropy, that is joint entropy or information in x and y is greater than or equal to information in x, information in either x or y. All right. So, the information, the joint information cannot be lower than the information in the individual sources. Okay. That is also intuitive, and this property can be shown. Okay. Now, something even more interesting is the fact that if you look at h of x plus h of y, this is equal to, this is equal to 2 plus 1.75 equals 3.75, which is greater than h of x comma y, which is equal to simply 3.375, correct. So, what you are observing is h of x comma y, the property that you are observing is that h of x comma y is less than or equal to h of x plus h of y. And this is a very interesting property. What this says is the joint information in x comma y is less than the sum of the information in the individual source. Okay. So, what you have seen previously is that the information is greater than the information in that of the joint information, joint entropy is greater than that of the entropy in either source. But what this result is also telling us, the next result is that the joint information is less than the sum of the component information, that is, it is less than the sum of the entropies of the constituent sources. Okay. So, the total information, joint entropy or total information is lower or equal to the sum of, or rather the sum of entropies the sum of the entropies of the individual sources. So, this is an interesting problem. So, while the joint entropy is greater than the entropy of either source, the joint entropy is less than or lower, less than or equal to the sum of the entropies of the individual sources. Okay. Let us try establishing this result. Okay. This is an important result. So, let us try establishing this. We have, well, from our definition, we have, these are information theory contains several such interesting inequalities. So, we have h of x y is summation over I, summation over j, probability of Si, that is x equal to Si, y equal to Rj. I am simply writing a probability of Si comma Rj 1 over log to the base 2 1 over probability of Si comma Rj. H of x equals summation over I, probability of Si log to the base 2 1 over probability of Si. Now, I can write this using total probability rule, correct. I can write this using the total probability rule. Remember, we have already seen that. I can write this as probability of Si is nothing but summation probability over j. So, each Si I can also, so each Si I can also sum over j, probability of Si comma Rj, because times log to the base 2 1 over probability of Si, because look at this, this quantity here is nothing but this is equal to probability of Si. This follows from total probability rule. Okay, because we have seen that probability of Si, each Si is nothing but I can sum it. I can take the joint probability Si comma Rj and sum the probabilities corresponding to all possible Rj's, all possible values of the index j. Okay, that is, this follows from that is equal to the probability of Si, and that follows from the total probability rule. Similarly, we have h of y is summation j probability of Rj log to the base 2 1 over probability of Rj. Now I can write the summation over I using the total probability rule. This is probability Si comma Rj log to the base 2 1 over probability of Rj. Okay. And now if you look at Hxy minus Hx minus Hy, you will see this is nothing but, well, summation over I comma j probability Si comma Rj log to the base 2 1 over probability Si comma Rj minus, so this is your Hx comma y minus summation over I comma j probability of Si comma Rj log to the base 2 1 over probability of Si. This is your Hx minus sum over I comma j probability Si comma Rj log to the base 2 1 over probability of Rj, and this is your Hy. And now if you can see, if you can take this probability of Si Rj common, you will see this is nothing but summation of over I comma j probability of Si comma Rj into log to the base 2 1 over probability Si comma Rj minus log to the base 2 1 over probability Si minus log to the base 2 1 over probability which is equal to, well, summation over equal to summation over I comma j probability of Si Rj log 2 to the base probability of Si probability of Rj divided by probability of Si Rj. Okay. So, this is the final expression we have for h of x, I am sorry, h of x comma y minus h of x minus h of y. And now you can see this is nothing but basically, correct, and I can write this, if the double summation is confusing, I can simply write it as a single summation, summation over all possible values of I comma j probability of Si comma Rj log to the base 2 probability of Si into probability of Rj divided by probability of Si comma Rj. And now you can see this is of the form summation over I pi log to the base 2 xi, and we have seen by Jensen's inequality this is well pi f of xi is less than or equal to f of summation over I, because log is concave, correct, because the log is a concave. This is basically Jensen's inequality. We are again using, or rather going to use, Jensen's inequality, since the function log 2 to the power, since log to the power ax is concave. And therefore, what we were going to have, so what we have seen is Jensen's inequality, we have summation pi f of xi, that is f, if f is a concave function, we have summation pi f of xi is less than or equal to f of the function of summation pi xi, where of course the pi's are probabilities, that is they are positive, they are non-negative quantities and they sum to 1. That is, of course, it goes without saying that the pi's are such that each pi is greater than or equal to 0 and summation of pi equals 1. Okay. And therefore, what we have is, if you can look at this, you have I comma j probability Si comma Rj log to the base 2 probability of Si into probability of Rj divided by probability of Si comma Rj by Jensen's inequality. This is less than or equal to log to the base 2 summation I comma j probability of Si comma Rj times probability of Si probability of Rj divided by probability of Si into Rj, and now you can see this probability of Si comma Rj, this cancels, this is equal to log to the base 2 summation I comma j. Now you can write it as summation I and summation j, split it into two summations, probability of Si and product of probability of Si probability of Rj, which is nothing but, if you look at this, this is log to the base 2 summation over I probability of Si into summation over j probability of Rj. Now you can see the summation of probabilities by total probability rule, this is 1, this is 1, so this is log to the base 2 of 1 and which is 0. So you can see this is equal to log to the base 2 of 1 and this is 0. And therefore, the net result that you have, remember this is all a simplification of h of xy minus hx minus hy. So the net result that you have is h of xy minus hx minus hy is less than or equal to 0, where we have employed Jensen's inequality to derive this result. Alright. So we have h of x comma y minus hx minus hy less than or equal to 0. Okay, and this is simply an application of some simplification using total probability rule and also basically by using Jensen's inequality, which is very important, as you will see, that is in information theory this inequality is used extensively to derive various interesting properties such as We have also seen this in the context of deriving the maximum entropy, that is the source, that is the probability density function of the probability mass function for the symbols of the source, which maximizes the entropy of the source, and we have seen that the maximum entropy occurs when all the symbols of the source are equiprobable. Okay. And now this has helped us derive this result, that h of x comma y minus h of x minus h of y is less than or equal to 0, which basically implies that, well, h of x comma y less than or equal to h of x plus h of y. Okay. So, that is the interesting part about this. Okay. So, joint information or joint entropy is less than or equal to the sum of the entropies of the individual sources. Alright. So, what we have seen in this module is we have further seen refined this notion of entropy. Alright. We have seen the properties of this joint entropy earlier. So, we had earlier defined joint entropy. Alright. We had calculated joint entropy from a simple example. We have also seen that the joint entropy is greater than or equal to the entropies of either source, right, entropies of either of the individual sources. Further, the joint entropy is less than or equal to the sum of the entropies of the individual sources, and this fact we have formally verified by proving it, and proving it with the aid of Jensen's inequality. Alright. So, let us so we will stop this module here and look at other aspects in the subsequent modules. Thank you.